Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This video is all about the difference amplifier. This is a core function block of our beloved and often used operational amplifier. But more than that, it is a core part of the Gilbert cell, which is used as a voltage-controlled amplifier, a balanced modulator, and, well, a lot of other things. The current source is one of the prime functional components of the difference amplifier. I'm not going to be providing a detailed description of a current source in this video. I covered that in the previous videos. So if you missed either of those videos, then I've put a link up in the corner and down in the description to the first video for you. I am going to be showing you my own bench experiment in this video too. Stay tuned as we work our way there. I have provided a formula sheet for you. The link to this is down in the description for you as well. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. So let's dig into this difference amplifier thing. So here is the schematic for the difference amplifier. It is unbelievably simple. 2 transistors, 2 resistors, and a current source. And the current source is made up of 2 more transistors and 3 resistors. So let's do a quick walkthrough. Our first assumption is that the 2 transistors are perfectly matched. This is an important assumption. The best way to accomplish this is to actually buy a device which has a pair of matched transistors in it. Trying to match transistors by using a curve tracer like I did is both time-consuming and, well, not as successful as you might think. Looking at the larger picture, we see that the difference amplifier has 2 inputs. It has a positive input and it has a negative input. We also notice that it has 2 outputs. It has a positive output and a negative output. Now, you can see that the positive output is associated with the negative input, and the negative output is associated with the positive input. Well, this is because each of the transistor stages are in the common emitter configuration, which is, by definition, an inverting amplifier. What makes this different is that these 2 common emitter amplifiers have their emitters tied together. These then are tied to a current source. What this current source does is limit the total current available to the combination of the 2 common emitter amplifiers. If one transistor draws more, then this forces the other transistor to draw less. The total combined emitter current at any point in time is equal to the current that is set by the current source. It is important to remember that the current source sources or sinks the same amount of current irrespective of the voltage across it. And so what this means is that the voltage on the emitters of the 2 transistors will essentially float voltage-wise as needed. So, what are the criterion for my bench experiment? The criterion for my bench experiment is that the positive supply voltage is going to be 12 volts. The negative supply voltage is also 12 volts. The current source current is going to be set at 1 milliamp. Inputs, that is the plus and minus inputs, are going to be sitting at 0 volts or at ground level. And the outputs, the plus and minus outputs on the collectors, will sit at half of the positive supply voltage at quiescence. So at quiescence, the collector currents of each transistor will be approximately 500 microamps because, well, they equally share the 1 milliamp of the current source. To establish a collector voltage of half the supply voltage, I'm using collector resistors of 12.1 k ohms. The current source's input on the base of the transistor is at minus 6 volts. So the final schematic looks like this. Now that we've had a quick tour, how does all this stuff work? When we look at this circuit, there are two modes of operation. First, there is the common mode voltage scenario. So what does this mean? Common mode. It means that we're putting the same voltage on both the positive and the negative inputs. So if I apply a positive 1 volt to the positive input, I also apply a positive 1 volt to the negative input. So what happens in our circuit? Well, remember the emitter current is limited by the current source, but the emitter voltage is not. And the base emitter voltage is relatively fixed. As a result, the increase in the emitter voltage tracks the increase in the base voltage. The base and collector currents remain essentially unchanged. You can see this in this LT-Spice simulation. I have varied the common mode voltages from a negative 2 volts to a positive 2 volts relative to ground. The yellow trace is the input voltage. The white trace is the emitter voltage. Notice how it perfectly tracks the input voltage just 635 millivolts below it. So how do the output voltages respond? Well, you can see here the plot of both the positive and negative outputs. They sit right on top of each other, tracking each other perfectly. They are changing from 5.997 volts to 5.999 volts, a change of a mere 0.03%. So how do we account for any changes? Well, with the emitter voltage changing and the collector voltage not changing, this means that the collector emitter voltage is changing. This change affects how the transistor operates to some extent, but nonetheless, it's only a 0.03% change. This isn't even worth considering for the vast majority of applications. Now, let's take a look at the other mode of operation. The second mode of operation is the differential mode. This is where the voltages applied to the inputs are going to be different. Now, we have to remember that no matter what we do, the total possible collector current of the two transistors combined cannot exceed the current of the current source. If the collector current of one rises above half this value, then the other must drop below half this value. Now, if we approach the analysis of this strictly from the standpoint of a high-level view of base current versus collector current of the transistors, assuming an absolute positive fixed base emitter voltage of 0.7 volts, then we will quickly find ourselves in a bit of a conundrum. We have the voltage on one input pulling the emitter voltage up, while the voltage on the other input is pushing the voltage on the emitters down. If, indeed, the base emitter voltage is an absolute fixed 0.7 volts. The reality is, it isn't. So how can this be? Well, while it is true that the BJT is primarily a current-operated device, as I've said in other videos, in this particular case, it is operating more on the basis of the base emitter voltage than on the basis of the base current. The base emitter voltage is not a fixed 0.7 volts. It is, in fact, proportional to the base current in a non-linear relationship associated with what is called the diffusion resistance of the transistor. This diffusion resistance forms the input resistance of the transistor and is equal to the thermal voltage, VT, divided by the quiescent base current, where the thermal voltage is generally estimated at about 26 millivolts at room temperature. Just like any resistance, it allows the voltage to vary, which in turn changes the current through it. In the end, without going into all the math associated with this, Here is the final conclusion for the relationship between the base emitter voltage and the collector current. I have to start by defining what is meant by the differential voltage. The differential voltage is the total voltage between the plus and minus inputs. So it is Vin plus minus Vn minus. With this defined, here are the equations for calculating the collector current with a given differential voltage, Vdiff, and assuming that the base current is small enough relative to the collector current to make it, well, more or less ignorable. The collector current of Q1 or IC1 is equal to the current source's current IQ divided by the quantity 1 plus the exponential brought to the minus differential voltage divided by the thermal voltage power. And the collector current of Q2 or IC2 is equal to the current source's current IQ divided by the quantity 1 plus the exponential brought to the differential voltage divided by the thermal voltage power. Now, let's just take a look at this just a tiny bit, little bit deeper. Well, if you guessed that the existence of the exponential in these equations tells us that this isn't a linear relationship, then you would be correct. With that said, there is a portion of the response which is reasonably linear. Now, it's no surprise that this linear portion exists around where the differential voltage is 0. So let's take a look at the response curves, which are based on these equations. The horizontal axis is the differential voltage in volts. I am varying the differential voltage from negative 200 millivolts to a positive 200 millivolts. The vertical axis is the resulting collector current in milliamps as calculated, assuming that we have a shared current source of 1 milliamp in the emitter circuit. You can see that the collector currents cross at the 0.5 milliamps point when the differential voltage is at 0 volts. Notice that when the magnitude of the differential voltage becomes great enough, all of the current goes through one of the two transistors. But the question we are addressing here is one of linearity of response. So to that end, if we zoom into the plot where the differential voltage is confined to plus or minus 30 millivolts, you can see that the plots appear to be, well, pretty much linear. Here, I have overlaid the absolute linear plots based on the data from plus or minus 20 millivolts of differential voltage. You can see how linear the collector current actually is. You can also see how it begins to diverge past a differential voltage of 20 millivolts. But what about the gain? Well, without going into a lot of math, the gain for a difference amplifier may be found with a very simple equation. The voltage gain of a difference amplifier in differential mode is equal to the current of the current source, IQ, times the value of the collector resistor, RC, divided by the quantity 4 times the thermal voltage, VT, where VT is estimated to be 26 millivolts at room temperature. The amazing thing about this is that the current gain of the transistor doesn't appear anywhere in the equation. So, for our bench experiment with the 12.1 k-ohm collector resistors and the 1 milliamp current source current, the theoretical voltage gain of our bench experiment would be 1 milliamp times 12.1 k-ohms divided by 4 times 0.026 volts, which gives us a theoretical voltage gain of 116.35. We will see how closely the bench experiment complies with this a little bit later. The last aspect of this difference amplifier is the input impedance. The differential input impedance is the impedance as seen between the two base connections of the two transistors. Again, we come to a very simple equation. The differential input impedance is 2 times the input resistance of each transistor, R pi, or the diffusion resistance. As I said earlier in this video, R pi is the thermal voltage, Vt, divided by the quiescent base current, IBQ. And the thermal voltage is often estimated to be 26 millivolts at room temperature. First, let's calculate our estimated quiescent base current. So for our example circuit here, where the collector current is half the current source current, or 0.5 milliamps, the current gain of the transistors is at about 100 in our present operating mode. So the quiescent base current would be 0.5 milliamps divided by 100, or 5 microamps. Now we can calculate our transistor's input resistance, which would be Vt, which is 0.026, divided by our quiescent base current of 5 microamps, which gives us R pi is equal to 5.2 k ohms. So the differential input impedance would be twice this, or about 10.4 k ohms. This can be increased by putting an emitter resistor in the emitter circuit of each transistor. We would then enjoy the benefit of a higher input impedance. The transistor's input resistance now would be R pi plus the emitter resistor value times the 1 plus the current gain, or HFE. If I were to use an emitter resistor of 50 ohms and our HFE was 100, then we would have an input resistance of 5.2 k ohms plus 50 times 1 plus 100, which gives us 10.25 k ohms. And the differential input impedance would be twice this, or 20.5 k ohms. So we've doubled the input impedance of our amplifier by adding this 50 ohm resistor into the emitter circuit of each transistor. The trade-off is that the overall gain of the amplifier would decrease because the emitter resistors act as negative feedback to the common emitter amplifier. The larger the emitter resistors, the lower the gain. In my simulation in LT Spice, the addition of these 50 ohm resistors into each transistor's emitter circuit more than halved the overall gain. So, how did my bench experiment perform? Well, here is the bench experiment. You can see here the current source with its 2 transistors. This resistor is the input to the current source. These other 2 are the emitter resistors associated with each transistor in the current mirror. Over on the other side of the protoboard is the differential amplifier transistors themselves. These resistors are the 12.1 k ohm collector resistors. Here are the input wires, which are connected to my signal generator. Following this up to the signal generator, you can see that my signal generator is set to produce a 10 millivolt, 1 kilohertz signal from each output. The second output is configured to be 180 degrees out of phase from the first. So how does this look on the scope? Well, you can see here that when the differential input voltage is 10 millivolts, that's at this point here on the screen, the output voltage is at 1.101 volts. This means that our voltage gain is 1.101 volts divided by 10 millivolts, which is the differential input voltage, which gives us a gain of 110.1, and this is also 40.8 dB. Now, that's nice. Now, as you may recall from earlier in this video, the theoretical differential gain of this amplifier is 116.35. There is only a 5.5% difference between theory and practice on this one. Of course, if we consider the differential voltage gain using both outputs, the voltage from here to here, well, then the voltage gain would be twice this because the voltage difference between the two outputs is twice. This gains us an additional 6 dB of gain. Well, hopefully this has given you some fuel for experimentation and a greater understanding of the very useful difference amplifier. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.